George shows up late.
He's pretty shy and late.
Looks like it's late.
Shocking. We're late. Well, exactly 12 o'clock at night, so. This is going to be like 30 minutes of Instagram waiting for Dr. Lee. Is that execution time? Yeah.
We were expecting you in the office.
Oh, I didn't. Yeah, it just said come to Salazar 2016.
No, my letter said come to 2016.
This is 2016, isn't it?
Yeah, that's where that's right. It says, please we can on campus and then for the fact that
Oh, okay.
Everybody's bunched up over there.
Okay.
And we need to fill out some paperwork.
So like an NDA or an NDA or something.
You'll see them after lunch.
Okay.
We were just discussing whether or not you should lose points for being late. Yeah, you're the last one.
Oh, you have one.
I almost have it. I think everybody deserves a freebie now.
Yes. Well, okay, ladies and gentlemen, welcome to our colloquium. Next week, next Thursday, will be Bill Kendrick. And if you don't know his name, you should know him because he's the inventor of Pax Paint, paint programs for little kids. And more important than that, he was one of you. He was a student here, graduated, and now lives in Davis. That's next week. Today I would like to introduce you to Mr. LeBrun, who is going to dazzle you with how to shave with Einstein's tools. Let's welcome him.
Okay, well, thank you. Does everybody hear me okay? Okay. So I sort of assembled a bunch of material. I guess George likes to have me come up and kind of shake things around a little bit. That's usually what I do. And I'm not sure exactly which parts are going to be more interesting or less interesting. So we'll just kind of expand and contract to fit. Kind of doing that however you see. If we have a little time left over, we can maybe have some questions or talk a little bit at the end. But it never seems there's more slides than there is time. So you probably maybe heard of Occam's razor. Occam was this medieval logician, William of Occam. And he's certainly worth checking out, but we're not going to talk about that today. And people usually say Occam's razor, says take the simplest answer, the simplest possibility. Actually, he said something a little different. He said it in Latin, and what he said was entities should not be multiplied needlessly. But we don't really we're not going to talk about multiplication much until we get to the arithmetic session. So anyway, Einstein sort of extended it. He said everything should be made as simple as possible, but no simpler. And I just found that a really interesting thing because how do you tell when you're making something too simple, right? When do you cross over the edge? And just what does it really mean to make something simple? So I thought I'd just kind of think about the idea of simplification a little bit. So start on the left here with a tricycle. Okay, that's got 3 wheels, right? Well, how could we make a tricycle simpler? Anybody want to hazard a guess?
Turn it into a pogo stick?
Well, that's one route. That's a little extreme. We'll talk about the bottom row, but obviously you could take off one wheel, right, and you could wind up with a bicycle. And you could make that even more simple by taking off another wheel, and you wind up with a unicycle. Now, the interesting thing about that simplification in some sense, but you also notice they get harder and harder to ride. So there's sort of some kind of space of trade-offs there, and so simplification really isn't very simple. And when you look at some of the radical possibilities, you can take all the wheels off, and you wind up with maybe a pogo stick, or maybe a bike frame that doesn't have any wheels and doesn't go anywhere. You can do completely strange things like get rid of the entire frame and have nothing but a wheel. You can have some strange device that headless people can use to roll around, and you can get rid of almost everything except the pedals, right? And that's another kind of simplification. So it's not clear any of those are necessarily too simple, but it does sort of raise the question about what do we mean by simplification and what are we simplifying? Certainly not bicycles. Now, I would suggest that Einstein was a physicist, and you might say, well, he's talking about physics, right? But you can't really simplify physics. Physics just is, right? Electrons and gravity and things like that are just whatever they are. So what he's really talking about is simplifying theories or simplifying models. And models are something that I find particularly interesting from a lot of different viewpoints. And I think it's always worth going in and looking at the models that we set up, especially our unconscious assumptions that underlie those models, and say, well, what happens if we tweak this? Is this part necessary? What happens if we change it? And obviously, if you sort of go down the main line of making things simpler by taking off wheels, you sort of get that progression, but you could also go down the pogo stick direction. So Now I'm going to jump in a completely different direction. How many people are familiar with Magic the Gathering card game? Okay, so we maybe got even some players here, right? I'll describe it just very, very briefly. It was one of those things that never got on my radar, right? I'd see kind of, people playing it and stuff, and I never could figure out what the point was until I realized that it's actually a kind of programming. And it's a very unusual kind of programming, and I'm continuing to study it. I've had discussions with Don Knuth, who actually wrote a paper with the inventor of Magic the Gathering. Unfortunately, never got published. And the thing that's weird about Magic the Gathering is, there's all these sort of, cards and, wizards and stuff like that. But that's not really the important part. There's just basically some little card game there. And it's beautifully designed. They spend huge amounts of money. There's thousands of these cards. They pay artists and all kinds of other people, novelists to write novels about the world that this is in and so forth. But it all comes down to basic gameplay. And there's stuff on these cards, like you'll see there's numbers and little symbols and they're different colors and stuff like that. And that all has to do with the basic mechanics of playing Magic the Gathering. I won't even go into that. You can look into it if you get interested. But the thing that's really, really fascinating is the stuff that's printed on those cards. Basically, every card in Magic the Gathering is an exception. You could just play some vanilla game like poker, but what if on every poker card you had something printed that said, okay, now you've got to throw away all of the hearts in the deck, or suddenly sixes have become super powerful and beat everything. And so it's what really happens, the programming part of Magic the Gathering is that people construct decks. And that's why there's a whole market for these cards, whether they're online digital assets or whether they're physical cards. There's some people collect them for the pictures and stuff. I don't much care one way or the other about that. But there are these rules and restrictions and constraints on how you can put together a deck. And this causes what happens is when the decks interact that two people have constructed, their theories and their models about what's going to go on wind up in collision. And so it's sort of like as though you had to write a program in a sort of event-driven system in a deployment environment, say, maybe something's going to go out in the battlefield. It doesn't know what it's going to encounter. It has limited resources, and so you can't make a deck, for instance, that has every card in it. It would be too big, and it would be unwieldy. And one of the things that people learn very quickly is if they try to make a really big deck, they never draw the card they really need right at that moment. So it's something that I think is very colorful and very strange, and it's an unusual way of thinking about programming. So I wanted to sort of see if maybe I could sort of cut out some of the complexity, although you can probably learn to play with somebody in about half an hour and have some fun with it, but maybe it's not your cup of tea. So I tried to sort of begin to, can we get the top down a little bit? Projectors are a way to do that. Anyway, this is a thing I call magic made mundane, or sometimes magic made stupid. And the idea there, can we pull the picture screen up just a little bit, maybe? So, yeah. Oh, I see. Just roll it upwards. Is there a control for that?
There's no way to change anything, please.
Okay, well, we'll lose the top of my titles, but anyway, that doesn't matter. So what I've been kind of working on, and hopefully this can eventually go from something that's done with physical cards, I tried to figure out how you do this kind of thing with an ordinary deck, how do you get rid of all of the sort of Dungeons and Dragons elements, and still get the basic functionality. It turns out it's harder to do than you might think. I'm still not happy with the stuff that we've come up with. At this point, it turns out that with the rule set we've got, what happens is one player gets an advantage, and then that advantage snowballs in a sort of kind of a boring game because of that. So you don't get those reversals of fortune and stuff that create a narrative and make for a fun game. But the other thing is the other sort of objective of doing this is once there's something that sort of halfway works with physical cards, the idea would be then to transfer that into some kind of open source development platform that people could work on so that you could experiment with the space instead of going to Wizard of the Coast and buying their card decks and things like that. I think it would be interesting to continue to delve into this weird, random kind of situational programming. So that's just an example of kind of one of the sort of things you can do with simplifying things. And so just again as a takeaway, when you look at something that exists, it's possible to go back and twiddle with the assumptions and say this is all very colorful and interesting, but what happens if I reduce this down to its bare elements? What parts are really important? Somehow or other, I eliminated something that made gameplay work better, and I still haven't figured out what it was yet. So that's just an example. I'm not going to go too far into that. So I'm going to switch gears a little bit and give us a little more time for this one. And talk about, I'm actually going to switch to another presentation. Okay, so we've got some size issues here still. I'll scroll for you. So I started looking at some of the simplest parts of doing arithmetic that we're taught in school. And there's a lot of different pieces of those algorithms. But one of them is the carries. And the reason I actually started looking at carries was quite some time ago, where I was looking at binary arithmetic. How many people are familiar with how binary addition works? Okay, with the bits and stuff. Okay, sometimes it's good to make sure people aren't completely unfamiliar with that. So what happens? You XOR the main bits together, and then you AND, and you get the set of carry bits, and you just shift them over one, right? And you repeat. So that's kind of a recursive definition of binary addition. I think last time I was here, I talked a little bit about that. And I asked myself, what happens if you shift them over two? Okay, and it turns out that something you can play around with, but it turns out what happens is that you wind up modeling, instead of ordinary arithmetic, you model arithmetic in what's called an extension, where essentially you're working in base square root of 2, okay, which is kind of weird. But it has some use, and you can, for instance, factor things. A number like 7, for instance, is not a prime in that number system because you can factor it into two pieces. So that was a case where you fiddle with something that the computer does in a very mechanical way, and then step back and say, what is this a model of? What have we actually created here? And that turns out to be kind of hard. A lot of times what we do with the computer is we're sort of oppressive, right? We're the oppressive masters of the computers. Someday they'll revolt against that, but we go and we say, well, we know what we want you to do, and we want you to be the model for this. And a lot of effort is put into that kind of thing. But what we often don't do is step back and say, well, what can the computer actually do? What happens if I just put a random bunch of instructions in? Well, usually it's just gibberish. But it's the model of something. And so sometimes if you do that in a disciplined way, we find out that there's potentially something useful that it's a model of. So, and I have to give some credit here. Oh, that's neat. You scroll right off the page. That's unusual. How many people here have heard of Martin Gardner? Just a few. Most of us older. Martin Gardner was this amazing science columnist. He wrote for Scientific American for a long time. He had a column called Mathematical Games, and it had a huge motivating influence on an entire generation of people. And it's sort of sad that people aren't as familiar with him as they might be. He died last year in his 90s, and we'd actually been writing this paper with my two co-authors who were at AT&T Shannon Labs. And we thought, well, this is just the sort of thing Martin Gardner would find interesting and amusing. So we started writing it, and unfortunately he died. We've done some further work. If you guys are interested, later you can come up. This is actually the first of 3 papers. This is the one about this arithmetic, and this is the one about another one called dismal arithmetic, and there's going to be a third one. So let's see. Let's move on here. Boy, this is tricky with the scrolling.
I think you could just actually launch it, it'll fix that.
Oh, I see. Yeah. All right. Good idea. That's better. Good. Okay. So arithmetic we learned in school. So I'm not going to do this in binary. I'm going to do it in decimal. Decimal's sort of a random thing to work with, but it actually lets you kind of understand things in more generality. I have a friend, a mathematician, who says, decimal notation is just a way to encrypt the truth, but I'm not quite that extreme. Anyway, when you do arithmetic, you do an addition, just like you're taught in school. 9 plus 4 is 13, so you write down the 3, and you carry the 1, and you say 1 plus 1 plus 5 is 7. Okay, so the parts of this that involve carrying, I've highlighted in yellow. It's a little harder to show what's going on in the multiplication over there, but again, there's a color coding, and there's actually 3 colors. There's a green, a yellow, and kind of a yellow-green that shows up in those 9s down there. So they're all getting affected. Those are the places that the carrying is affecting the answer. We all learned this in school, right? It's an interesting exercise, for instance, to prove that it works and that it creates a model of integer arithmetic, because this is a bunch of mechanism with, calculating with pieces of data, numbers, digits, and who's to say it actually gets the right answer? Right? That's something they don't do in elementary school is actually prove that arithmetic works, but it's worth doing. So we decided, well, given the state of everything, maybe we should just see what happens if you just get rid of carries. What does that do to arithmetic? This is a little joke based on an old advertising slogan for, I guess it was some kind of toothpaste. And they said the old slogan was 4 out of 5 dentists recommend some toothpaste for their patients that use toothpaste or something. We're going to say 4 out of 5 computists recommend carryless sums for their patients that do sums. So that's just our little advertisement. So here's the new improved carryless arithmetic, right? Grayed out the stuff where the carries were. And it's interesting. You see, you get something else. And now the question is, what the heck is this thing? What can we learn about it? And so, for instance, here I've sort of got it kind of bluish gray. It's hard to see to indicate that we're ignoring that carry up on the top. And so in this particular kind of carryless arithmetic, the sum of those two numbers isn't 473, it's 463. Okay, and then there's a computation down here, again, that's kind of interesting. And you'll notice, for instance, there's a little 0 in front of the 550. That's to show that we're ignoring the carry that would have fallen down there. So we get a different answer. So now we've done something that's actually easier, right? The computer, doesn't have to mess with the carrying. You don't have carry propagation delay. You don't have to design circuits for it. What the heck is it, though? Okay, and so I keep finding those kinds of questions come up when you simplify things. Sometimes you sort of pull off the cover and there's a whole bunch of other stuff under there. So here's some more weird examples. You can actually get situations where the number appears to get smaller. Now the question is, are these really numbers? Do they represent magnitudes or quantities? Well, not so much, right? They're just strings of digits and symbolic. And so we're already sort of venturing into some more abstract realm. But I thought I'd show the addition and multiplication tables. This is what happens when you work with digits, right? You just get the usual kind of mod 10 thing happening for addition, and multiplication gives that table over there. It's worth looking at that table a little bit. And let's see, any of you people mess around with abstract algebra or done any of that kind of stuff? Okay, a little bit. So you set up tables like this and you try to understand, what is this operator? What are we actually computing here? And there's some weirdo things in there. I mean, sure, 0 times 0 is 0, but look at the 5 row there. You get this weird alternating pattern. What's that all about? Or if you multiply anything by 2, of course, you get an even digit. But if you multiply anything by an even number, you get an even number. So that's, they begin to see some patterns. And so by looking at that, you say, well, what is this stuff we've created by simplifying ordinary arithmetic? And so we sort of look at this, and I won't get too deep into this because it's kind of getting more into abstract algebra. But basically, we find 0 still behaves like 0, right? You add it to something that doesn't change. 0 behaves also under multiplication like you'd expect. 1 behaves like you'd expect. 5 and all the even digits, though, divide 0. And so you're in a world, mathematicians sort of, seeing 0 divisors is one of those warnings, like suddenly there's, vampires around or something. And you get all these other different things. One of the strangest things is that when you multiply by 1, 3, 7, or 9, 9 kind of acts like -1, and 3 and 7 kind of act like I and minus I. So in some strange sense, here we whack the carries off of decimal arithmetic, and it's starting to exhibit behaviors that are more associated with complex arithmetic. So clearly we found some stuff there. So there's a very general theorem. It's very simple, easy to prove, but it basically says if what you do with single digits commutes and associates and distributes, then so that'll also be true when you go to multiple digits. And so that's all true. There's some really interesting sequences you start getting when you mess with this. I don't know if you're familiar with Neil Sloan, my co-author's got this thing called the Online Encyclopedia of Integer Sequences, and there's hundreds of thousands of sequences in it now that people have documented. It's a great reference resource. There's been a number of discoveries where people have had a sequence of numbers come up in their research, and then they'll jump into the OEIS and find out that there's all these references or previous research. So it's a very interesting way of indexing human knowledge, at least the kind of knowledge you can represent with number sequences. But anyway, with the carryless mod 10 stuff, when you add a number to itself, you get this, instead of just the regular even numbers, you get this funny looking thing with of course, all even digits. The squares act in a funny way, right? You go 1 times 1 is 1, 2 times 2 is 2, 3 times 3 is 9, 4 times 4 is 16, but you throw away the carry, so 4 times 4 is 6, right? And in fact, it's palindromic and comes back to itself. But then when you get to 10, it's a multi-digit thing. 10 times 10 is 100 and so forth. You can see familiar squares there up until you get to like 186 and then 105. There's sort of funny stuff. So there's a lot of structure there, and it's kind of mysterious. Same thing with primes. What prime number in ordinary arithmetic is one that doesn't have divisors, right, other than a unit. And so in this arithmetic, you have primes, but they're not the same primes. So with a lot of work, which you can look at in the paper, you can begin to come up with some interesting actual results about this world, and they're different than the ones you get for ordinary arithmetic. Like, how many squares are there for k digits? Well, we actually managed to find a formula for that, and it's this weird-looking thing, but it's definitely not as weird as it gets. And how are you going to understand this? So I'm just going to talk about this until we run out of time for this sprint. But so eventually, what you can realize is that those 10 symbols that we're using, the digits, actually are better thought of as some number either 0 or 1 and another number 0 through 4. And so there's this mapping between the digits to these pairs of digits. And now all of a sudden a whole bunch of heavy machinery comes in from mathematics that allows us to understand what that thing is doing. So eventually we were able to characterize what the primes are. And you can read that if you want or look at the paper. I think I don't need digging into it. But by breaking them into the part that's sort of the even part and the 5-ish part, we were able to tame this thing. Now again, this is a whole bunch of deep mathematics, but how do we get here? We started by taking ordinary school book arithmetic and just whacking a piece off of it and making it simpler. So are we sort of in the borderland here of Einstein's prohibition, right? Are we making it as simple as possible? Are we making it too simple? I mean, what does it mean when you make something simple and it gets more complicated? Let's see. Actually got a formula for the number of primes of k digits in this world. There is no such formula in ordinary arithmetic. So that's also kind of interesting. And so there's more of these things. So there's, for instance, the middle one there is what I call dismal arithmetic, sort of a pun on decimal. Our second paper, which is longer and hairier, is about that. And that's what we did there was say, instead of doing this mod 10 thing with the digits, let's simplify addition even more. Let's say addition is that you just take the larger. That's it. It's just max. So 5 plus 4 is 5, and multiplication you just take the smaller. 5 times 4 is 4. Turns out that you open up this huge, interesting space of a completely different arithmetic, and you can even push the envelope a little further. Research question is just if you look at just this simple set of operations, how many actually distinct kinds of these arrayless arithmetics are there? It seems like there's a whole bottomless sea of them. I'm not going to go through all of these. So there's one that was weird that we were looking at called topical arithmetic, where you wind up having a difference between 0 and double 0. So I guess if you need an arithmetic to model roulette wheels, that's useful. But these are just integers. You can also look at other things, fractions, partitions. How many people in here are familiar with what a partition is? Okay, a couple of people. So a partition is just, some numbers that you can add up to get another number. So those numbers are called a partition. So a partition of 5 is, 1, 1, 1, 2. And I find it really interesting that, you don't even need to know multiplication in order to study or learn about partitions. They can teach it to kids before they teach them multiplication. There's all kinds of interesting, deep, wonderful stuff there. And for the most part, no one even looks at that. And I find that sort of a loss. So have a look at those. And I think we fell off the end there, so that's a good thing. So I promised to talk a little bit about Leibniz. He was a smart guy. He was a really smart guy. Him and Newton, I don't know if you know, had this big fight about who invented calculus. And had very different philosophies and approaches. Some of the best ideas came from Newton. Some of the best notations and procedures and algorithms came from Leibniz. He had a whole lot of other interesting philosophical ideas. And of course, Newton was an alchemist as well. So these guys have more depth than you sometimes might want to give them credit for. The thing down underneath Leibniz's portrait there is a calculator that he designed. So he was actually into computing machinery, back in the era where people wore powdered wigs. And over on the other side is an iPhone. Now, I was thinking about what if I was like having tea one afternoon with him. And he said, well, so tell me about these computers, right? They're really interesting. And I said, well, I'll recap the history. And so you start talking about, I don't know, Johnny von Neumann and the World War II and all of that stuff. And up to a certain point, it's easy to explain to Leibniz what we were doing with computers, right? Essentially, they were calculating. They were calculating engines. Now, somewhere in there, we got personal computers and internet and high bandwidth displays. And I'm at a loss as to how to explain what it is we're doing anymore with computers. We just have these things. What is it? Is there a theory? Is there a model for this? We've just accepted a whole bunch of stuff that's happened in the last several decades. But maybe this is another case where we want to maybe go back and look at stuff. And so I'm a little bit I guess I should go into slideshow mode here. That was a bad idea. So I'm in an interesting position to think about some things, namely the Macintosh. Originally, the Macintosh, before Steve Jobs grabbed it by the throat and turned it into something commercially successful, was a research project. There were 4 people on it. One of them was me. That's me then, down in the corner. Jeff Raskin, who invented it, he's dead. Brian Howard was also part of the project. He died last year. Burl Smith was the hardware guy, is still around. He went completely crazy, in my opinion. And there's me, and I was realizing we're dropping like flies. Maybe it's time to go back and think about it. But it was just this little research project over in the corner of some building in Cupertino, and the real stuff was happening on the Apple II. And so I started thinking a little bit more about what we were doing back in the day. So this is just some documentation on that. It says Macintosh Research Project. It's got our names. Down here it says, this is a research project, not product development. And we have a Macintosh processor, display, and keyboard running in the lab. So there was like this breadboard once, right? The Macintosh didn't just suddenly appear to Steve Jobs in some vision. It was something that people such as yourselves put together and made happen. And it was really crippled by modern standards. Basically, the entire display was just 256 by 256 pixels, black and white. That's it, and that was half of the memory. Okay, the other half we had to do everything else. So. We're now regularly wallowing around in gigabytes of memory and all of this other processing capability. I could explain to Leibniz that because it's really simple, but I can't explain what we're doing anymore. And I think that's something you want to think about because we have about 1 million times more resources to work with than we did on the original Mac project, and that spawned the Mac. So, and people kind of got so busy making it a commercial product and so forth. We kind of forgot to go back and think much about what it is we're actually doing. Steve Jobs wanted to take over the world, but the rest of us sort of got involved in the details of implementing that. So what can you do with 1 million times the resources that the people who sort of rubbed sticks together and created the first Mac had? Ought to be 1 million times more cool, right? So let's figure out how to do it. So this is some more debris I just thought I'd gather up. This is essentially the napkin that Burl drew the diagram of the hardware for. Just that's it, and it was drawn by hand with pencils on a piece of paper. So all of the heavy-duty machinery that we always think we need, isn't necessarily a requirement. You just have to take some resources and have some inspiration on how to organize it. So
Research notes.
I'm sorry.
Research notes, right?
Well, we. So we only had Apple IIs to work with most of the time. And so what we'd have to do is write these memos to each other. We're actually pretty more disciplined than a lot of research projects. And we'd go back and forth about design. And so this is a bunch of stuff that Jeff wrote, and then I scribbled all sorts of red yelling stuff on this. What's really interesting about this particular thing recently, people have suddenly started looking at how does scrolls work, because we've got these things, right? And so does it mean that, and right here I'm having an argument with Jeff about, is it the window that's moving, or is it the document that's moving? Because depending on which way you think about that, when you pull like this, you either pull the document down and it scrolls that way, or you're pulling the window down, in which case the document sort of looks like it goes that way. And it's different on touchpads and other kinds of interfaces depending on which model you've got. Right now there's actually a lot of discussion going on about that. So that's an unexamined thing. What's scrolling in Windows? That's obvious, right? Let's see. So let's move on from this. This is just another example of, right, we're used to having graphics in order to, you do a wonderful PowerPoint presentation. Well, this is just some stuff I was doing trying to come up with a sort of graphical assist to a programming environment in that era. And you'll notice that this document is all held together with Scotch tape and hand-drawn stuff and hand-colored stuff. And that's because I did that, pasted it up, and then put it in the copy machine. And then we could put that in our document that we gave, Steve and Woz and people like that. Because there wasn't anything there. You couldn't just take something that already existed that had windows in it and show what it was going to look like. Folders, for instance, were a new concept that was just coming out of Xerox PARC. But that shouldn't stop you as designers, right? You should try to imagine the things that don't exist, not another version of the things that already exist. This has also caused me to pay some attention to what I call QWERTYs. And if you look at the top row of keys on your keyboard, there's these letters QWERTY. And this is actually sort of a collage that I collaged on top of. What originally was part of the slide talking about the evolution of all of the shift and control keys on the edges of the keyboard, but that's not that interesting. So there's some pictures here of early typewriters. Beautiful marketing presentations. And so does anybody in here know the alleged reason why the top row of keys is so crazy, or why the keys aren't? Okay, we got one.
It's so that people wouldn't type too fast and jam the machine.
It was the latter part, that they wouldn't jam the machine. Did you have?
Yes.
Okay. Yeah, so, there's these mechanical things, right? And they were sort of like pianos, except they had letters. And these arms would come up and whack the paper, right, with, type on them. And so it's a bad thing when they jammed. And, when I was a kid, play with real typewriters, but mechanical typewriters, they'd always be jamming. You have to pull the things apart and stuff. So they scrambled the heck up out of the keys, out of where the letters were, so that you tend to type with alternating hands. And I had recently been lectured by Don Norman about how, well, it's actually a good thing. But it's just this completely weird, arbitrary thing that got designed once, and it's just kind of frozen in our culture, and we don't come back to it. Remember, my late grandfather, when I was sort of working on the Mac, he said, well, son, what do you do these days? And I said, well, I work with computers. And he kind of looked at me and chuckled, because he'd started in steam engineering and moved over to the new wave technology, which was electricity. And he said, yeah, those things kind of just sprung up like mushrooms, didn't they? And I thought that was just kind of funny, because, things do spring up like mushrooms. But what it did was that also the computers now has carried forward this strange design. And so the thing that's going to be really hard to explain to Leibniz is why we're doing it still on an iPhone, right? Because there's no mechanical arms that are banging into each other. We don't even have, buttons we're pressing anymore. We're hunting and pecking, and there's this really peculiar scrambled up thing. And that will probably outlast the human race. That completely strange QWERTY. So it's worth going back and looking at these things. I don't necessarily, people have tried to suggest different layouts and stuff, and it's usually more trouble to learn the new one than it's worth. But that's just kind of an example of how design has a kind of persistent quality. So I'm going to switch to something completely different. I told you I was going to do this. Reset here. So this is going back to this business about modeling. And I'm going to switch from talking about hardware design, interface design, to talking about object-oriented programming. Now, how many people in here have done some object-oriented programming? Okay, good. Worried I'm in the computer science department. Nobody raises their hand. I'm probably in the wrong colloquium. So object-oriented programming kind of presumes a model of the world, and it seems incredibly reasonable to all of us, which is that there's objects and they got properties, and so isn't that how the world is built? Well, we start taking the actual world apart and looking at how it's really built. What are things made out of? Right? Well, they're made out of atoms or light or something, and you get a little farther down, and they've got these things called particles. And what the heck are particles? They're actually the atomic components, the things that that physical reality is built out of, we're built out of. And so it's an interesting question of sort of how should we model that? And that's kind of what physicists try to do. Now, we've heard of Einstein, and we sort of imagine this cool guy with wild hair. Einstein actually got his Nobel Prize for some stuff about Brownian motion, I believe, which is ultimately based on quantum effects, right? The random motion of little tiny things. But it really bothered him. Quantum mechanics always really bothered Einstein. One of his kind of major projects for his whole life that he never really succeeded at was to try to come up with some way that would do away with the randomness that is inherent in quantum mechanics. And so he's had a famous saying, God does not play dice with the universe. It just was an article of faith with him. And so him and a couple of his buddies, Podolsky and Rosen, got together in 1935. And they said, okay, quantum mechanics is doing really good predicting things. Let's see if we can get it to predict something that just doesn't make sense, right? And we'll just prove that the whole thing is a mess. So they came up with this Gedanken, that means a thought experiment. And they published some paper, and they said, quantum mechanics, how could it possibly describe reality? Because if it does, this is what's going to happen. And that makes no sense. So, well, things kind of, there were a few people thinking about that, a guy named Bell and some other people, but most people didn't pay much attention to it until like the late 70s, early 80s. This guy, Alain Aspect, and some of his colleagues actually did some experiments with real electrons. And sure enough, quantum mechanics predicted what they did. They behaved the way that Einstein, Podolsky, and Rosen said they would, and of course, Einstein said it can't possibly be like this, it makes no sense. But the physics, actually, the electrons said, no, we really behave like this. And so, what are you going to do about it? And it's I think, a really important thing that people are maybe, again, not very familiar with that kind of calls into question assumptions that we make about a lot of stuff. And in particular, I'm going to show how it connects to object-oriented programming, or try to explain it. So just a real quick thing. The little cartoon down there is a picture of sort of from some publication that kind of shows the whole experiment. So there's two things and a detector in the middle, and or actually there's two detectors and an emitter in the middle. But I'm going to talk about it from the point of view of computer science. And so again, simplifying it, getting rid of a lot of the stuff. Yeah.
5 minutes.
Ooh, okay. Well, I think I really jammed that. Yeah. Okay. So real quick, get a particle. You can detect it. You get to pick 0, 1, or 2 as the component that it observes. You only get to do this once, and either it turns on a light bulb or it doesn't turn on a light bulb. It returns true or false, right? That's it. And so if you want to model it, I wrote some Java code here. Basically, there's this method, observe value. You give it a 0, 1, or 2, and it returns a true or false, right? Basic, straightforward object-oriented programming. There's also a rule that you can't look at it more than once, because basically once you look at it, you wreck it. That's just the physics. And then what they do is they say, well, let's create these in a special way. It doesn't matter if physicists know how to do it. That's called an entangled pair, or just any pair. We send both of the electrons to two detectors, and we get to set the detectors any way we want, and they either light up or down, right? So it's kind of like now you make two of these objects. They're related somehow, and you get to call these methods on them. Anyway, so we do it independently, and you can model that, and that's all fine and dandy. Model observations and write code. And finally we say, now let's just say that the particles have state. We flip a coin and determine whether it's going to be true or false for 0, true or false for 1, true or false for 2. Going a little faster. If you make these random enos and you do your experiments, you get a set of results, a set of statistics like that on the bottom. However, if you actually, there's a set of constraints that they're true or false randomly at 50%, and when the components match, the values match, right? So basically you make a copy with random contents and make a copy of it, and you'll get that statistic. What electrons actually do is they're entangled. And so they always match when you measure the same component, and they conspire to unmatch more than they should if they had state on the other component. So there's that third thing that Einstein said, this is the fly in the ointment, and actually real physical reality does. So as a result of all of that, you basically get to choose one of these two horns of the dilemma to be stuck on. Either you have to say that real things that the entire universe is made out of, pretty much, they don't have state. This whole idea of modeling them with an object is complete nonsense. Or you can say things have state, but then you have to give up causality. Basically, you measure one particle, and it somehow goes back in time and tells some other particle, oh, don't match me. And that creates some pretty serious philosophical problems. So I sort of had to spread over that kind of quickly. But I recommend, if you want to go through some interesting philosophical torture, go back and look at the EPR experiment and try to figure out how you create a model of it with object-oriented programming. I guarantee you'll find some interesting things there. So to kind of finish up, go back to Magic the Gathering. I happened to run into this card, which is it's actually called a tangle, and that's an entangled something or other there, and sort of reminds us again that sometimes when you simplify things down, they aren't necessarily. You maybe simplified them more than you expected and discovered that there's a lot more underneath that. So I think we've burned up all our time, right?
Well, maybe there's time for a question or two.
Right. Or I can give you an exercise to. I'll probably not enough time for that. You can actually experience being entangled. Maybe people want to stick around. I'll show you what that is later. It's a pair exercise to do with somebody else. But anyway, yeah. So questions, comments. All right. Going once, going twice. All right. Great, yeah, it's sort of, I try to throw out a whole bunch of different things. They're on archive. 3 papers, one of them's about something else. Unless there's high demand for it, we're welcome to promised to share them with somebody else. They promised to send me an email if you discover it. Yeah, I'll close it down here.
I was curious, like what you were talking about with these different forms of arithmetic. I mean, obviously my skills in math are not. I haven't studied math to any extent, beyond pretty basic calculus.
That's why I have
stuff,
co-authors.
I'm just curious, like when you're working on something like that, what are you hoping to go with that?
Well, I mean, it's partly just, it is kind of play, you know. It's like, well, you know, let me do this and see what comes out the other side. So it's kind of a creative process. You know, it's like you throw something on the canvas and it looks like something. So like the first couple of things I did, either they turned out to be knowing things or uninteresting things, and then you know you try a couple other things, and it's just the method's really simple. Simplify something.
Yeah, I just thought like some of those the mod 10, the addition and multiplication tables and stuff you showed. Like, it doesn't mean much necessarily, like at first glance, but just seeing the patterns and stuff. Really
Right, you can hear the signal coming back.
Yeah, there's something
under there. Yeah.
Maybe what, you know.
Well, enjoy. I gave somebody my papers.
Thank you. Appreciate it.
Sure. Thank you for helping. Whatever you do, whatever
Okay guys, before I pass the exams, does everyone have a Scantron?
Scantron, maybe.
Yeah. You don't have one? Okay.
Extra.
How much do you charge?
I just give it 3 one time.
Okay. Joe, I think in the back. Alright, thank you. Okay, so remember to read carefully the questions to make sure that your answers address all the different aspects of the question. The multiple choice, if you do them carefully, you should be done in at least half an hour. You can't be done with the multiple choice in 10 minutes. If you do that in 10 minutes, you haven't done a careful elimination process and you're likely to make a careless mistake. So take your time to go through all the different options. Do not rush to the multiple choice because sometimes the difference between answer A and B can be just one word. So don't miss that word. Yes?
How many questions are there?
30, like on the practice exam. And make sure that on the short answers, if I ask explain or why, right, you do provide some explanation because if you just say yes or no and I have no explanation, you won't get full credit for that question. So if I ask for show your work or explain why, or if I say describe, you have to be, you have to provide a complete answer to get full credit. Okay? So there's 2 versions of the test. So you need to sit next to someone who has a different version, and you'll see as soon as you get one that as a precaution based on past year's experience, I'm asking you to write down who you sit next to. And I'm not assuming anything about this class, you just as a way of covering my butt or cheating faces.
What's your name?
And you'll meet your classmates. Maybe that's a social introduction. So I can just run the middle. All the notebooks need to be off the table, on the floor, face down, yeah, make sure you write your name on the Scantron so that schedule the correct Scantron on your. You can write blue or white for the version. You don't need to write anything else, but I need your name. Oh, sorry. Yeah, you can start. Again, take your time, right? You have an hour and 15 minutes. So if you're done early, again, I'll say it one more time. Proofread your exam before you finish. So make sure that you address all the questions that on the Scantron you didn't skip one, and that everything is not broke down by one question.
So do they have limited time?
No, an hour and 15 is the whole class.
So yeah.
Yeah, you're right. This is so. I all have the multiple choice. If you do that elimination process and else, you should have stuff written on it. But I'm not going to look at it. It's more like for you to make sure that you've done the, you've thought about the question carefully enough to pick the right answer.